4.5 billion years ago, there was no Earth, no Sun, no solar system at all. Just an enormous, cold, almost perfectly still cloud of hydrogen and helium drifting through the outer arm of the Milky Way. And then something nearby died. A massive star collapsed and exploded in a supernova. And the shockwave from that death rippled outward across light years of space. When it hit our cloud, it did something that would ultimately produce every planet, every ocean, every living thing you have ever known. It made the cloud collapse. And what happened next is the most violent, beautiful chain of events in our solar system's history. Here is what almost nobody tells you. The formation of our sun and planets was not a peaceful process. It was catastrophic. Worlds crashed into each other at tens of thousands of kilometers per hour. Oceans of magma covered entire planets. The early solar system looked nothing like the orderly arrangement we see today. And yet, from that chaos, something impossibly precise emerged. A star that has been burning steadily for 4.5 billion years. 8 planets in stable orbits. And one small rocky world, positioned at exactly the right distance, with exactly the right conditions for liquid water to exist. By the end of this, you will understand not just how that happened, but how the sun manages to keep burning, why it will not run out of fuel for another 5 billion years, and why the energy warming your face on a sunny day started its journey inside a star as something far more fundamental than light. Let us start at the beginning, when the shockwave from that ancient supernova compressed our gas cloud. Gravity took over. The cloud began to collapse inward under its own weight. As it collapsed, it began to spin. This is conservation of angular momentum, the same physics that makes a spinning skater speed up when she pulls her arms in. As our cloud shrank, it spun faster and faster. The faster it spun, the flatter it became, spreading out into a rotating disk of gas and dust, like an enormous cosmic frisbee dozens of astronomical units across. At the center of this disk, where the density and temperature were highest, material was piling up rapidly. This central concentration would become the sun. In the disk surrounding it, something else was beginning. The disk was not uniform. Tiny particles of dust and ice and rock were constantly colliding, sometimes bouncing apart, sometimes sticking together. Over millions of years, these small sticky collisions built up larger and larger clumps. Pebbles became boulders. Boulders became mountains. Mountains became the first protoplanets, called planetesimals. Bodies large enough that their own gravity began pulling in even more material. This process is called accretion, and it was extraordinarily violent. Planetesimals smashed into each other at devastating speeds. Many were destroyed. A few grew dominant, sweeping up everything in their orbital path. These became the planets. Now here is where something remarkable happened, and it explains the dramatic difference between the inner and outer solar system. Close to the young sun, temperatures were so high that only dense, rocky materials could survive. Ices and gases were vaporized or blown away. So the inner planets, Mercury, Venus, Earth, and Mars, formed from rock and metal. Small, dense, and solid. But further out, beyond what astronomers call the frost line, temperatures were cold enough that ices of water, ammonia, and methane could survive. This made far more material available. Jupiter and Saturn accumulated so much mass so quickly that their gravity began pulling in hydrogen and helium gas directly from the disk. They became giants. Further still, Uranus and Neptune formed from those ices, becoming ice giants. The architecture of our solar system is essentially a record of temperature. Earth's formation took roughly 50 million years. In those early years, our planet was a very different place. It was covered in a global magma ocean, constantly bombarded by planetesimals and comets. One of those bombardments was the defining event in Earth's history. A Mars-sized body, which scientists call Theia, struck the early Earth at an oblique angle. The impact was so violent that it vaporized much of both bodies. The debris was thrown into orbit and gradually coalesced into what we now call the Moon. That same impact is thought to have given Earth its current axial tilt, which is responsible for our seasons. Everything you know about life on Earth traces back to a catastrophic collision 4.5 billion years ago. But while all of this was happening to the planets, something far more extraordinary was occurring at the center of the solar system. The young sun was reaching a critical threshold. As material continued piling up at the center of the disk, temperatures at the core rose to extraordinary levels. When the core temperature reached approximately 10 million degrees Celsius, something happened that had never happened in our region of space before. Nuclear fusion began. Here is what fusion actually is. At room temperature, atomic nuclei repel each other strongly. They carry positive electric charge, and like charges push apart. But at 10 million degrees, nuclei are moving so fast, with so much kinetic energy, that when they collide, they can overcome that repulsion and actually fuse together. In the Sun, this happens to hydrogen. 4 hydrogen nuclei, which are just protons, fuse together to form one helium nucleus. But the mass of that helium nucleus is slightly less than the combined mass of the 4 protons that form it. About 0.7% of the mass is missing, and that missing mass did not disappear. It was converted directly into energy, according to Einstein's famous equation, E equals mc squared. Because the speed of light is such an enormous number, even a tiny bit of mass produces a staggering amount of energy. Every second, the Sun converts approximately 600 million tons of hydrogen into 596 million tons of helium. The missing 4 million tons becomes energy. That is the equivalent of 10 billion nuclear warheads every single second, released continuously from a ball of plasma 1.4 million kilometers across. And yet the Sun appears to burn calmly and steadily in our sky. This is because the outward pressure from that fusion energy is precisely balanced by the inward pull of the Sun's own gravity. The Sun is in a constant state of equilibrium, a controlled explosion 4.5 billion years in the making. The energy produced in the Sun's core does not travel quickly to the surface. In fact, it takes an average of 100,000 years for a photon of light generated in the core to find its way through the dense solar plasma to the surface. It is constantly absorbed and re-emitted, bouncing in random directions, a process called a random walk. But once it reaches the surface, it travels through the vacuum of space at 300,000 kilometers per second. 8 minutes and 20 seconds later, it arrives at Earth. That photon, which began its journey during the last ice age as a nuclear reaction in the heart of a star, hits a leaf. The leaf absorbs it and uses its energy to split a water molecule, to pull carbon dioxide from the air, and to build a glucose molecule. That process is photosynthesis. That energy then moves up through a food chain. Every calorie you have ever consumed, every movement your muscles have ever made, traces back to a proton-proton fusion reaction in the core of the Sun. And here is what makes this even more extraordinary. The Sun has already been doing this for 4.6 billion years, and has enough hydrogen remaining to continue for approximately another 5 billion. It is less than halfway through its life. The violent, chaotic, catastrophic process that formed our solar system produced a star so precisely balanced that it will warm this planet for longer than multicellular life has even existed. The solar system began as a shockwave from a dying star. It became a spinning disk, then a collection of colliding worlds, then a stable system with a nuclear engine at its center, and at just the right distance from that engine, a small rocky planet developed liquid water, then simple chemistry, and eventually the capacity to look back at the sun and wonder how any of it is possible. The chaos was the point. Without the collisions, there is no mood. Without the mood, the axial tilt is unstable. The seasons are violent. Complex life may never emerge. Without the supernova that started it all, there is no shockwave, no collapse, no solar system at all. Every disaster in our solar system's history was a step in the sequence. And the sun, burning 4 million tons of itself into energy every single second, is still running that sequence right now.